All right. So today we're going to talk about prime numbers. And so yesterday we finished up talking about Abel summation and kind of our base tools for determining how big these arithmetic functions or these smoothed out arithmetic functions are. And we talked about a very important arithmetic function, the Mobius function. And we kind of did our first baby example of a sieve, which is sieving out to get square free numbers. There's an exercise in the problem set which asks you to do that sieve again in a slightly different way. I think that would be a very good exercise to do. And it also asks you to generalize it from square free numbers to k power free numbers. So what we're going to do today, this section is on prime numbers. In this section, we're not going to do any sieves. This is just going to be a bit talking about some results on counting primes that will be useful for us in the context of sieves. And then depending on how much time we have left today, we'll start talking about the sieve of Eratosthenes again, but in a little bit more detail than just the picture proof. So this section, we're just going to start with the prime number theorem. And I don't know if you are attending Alvaro's lectures on computational number theory, but he already talked about this theorem a little bit when he was doing some work with Sage. The prime number theorem says that if you look at the arithmetic function that, well, gives you a 1 if the integer you're plugging in is a prime, and it gives you a 0 otherwise, and you smooth it out so that you're basically counting the number of prime numbers that are less than or equal to x, that function is asymptotic to the function x over log x. So again, what that means is if you take the quotient, the number of primes less than or equal to x, divided by x over log x, take a limit as x tends to infinity, that quotient is tending to 1. So I've got a little paragraph down here talking a little bit about the prime number theorem. If you've taken any courses on analytic number theory, most likely the prime number theorem was where your course was building towards. It's a big result in number theory. For a long time in mathematics, it was a big goal of number theorists to prove this theorem, or to get close to proving this theorem. And there's a lot of proofs of it now. We understand this theorem very well. Most of the proofs, including the ones that are the most accessible, use complex analysis in order to actually prove this result. Now, if that's a little bit intriguing to you, I definitely encourage you to pick up a book on introductory analytic number theory or join a course on analytic number theory, because the complex analytic techniques in number theory are very cool. But that's not going to be the direction we're going in this course. One of the reasons I wanted to do this course actually is that almost everywhere where you see analytic number theory introduced, it will take the route towards complex analysis, and I wanted to instead do the route towards sieve theory. Routes that don't use complex analysis tend to be called elementary methods in analytic number theory. So in the context of analytic number theory, the word elementary just means no complex analysis. There does exist an elementary proof of the prime number theorem. I think the most famous one is due to Selberg. But that is much longer to prove, and we're not going to really touch Selberg's proof in this mini course. You could probably dedicate an entire 4 or 5 lecture mini course just to Selberg's proof. But that's not what we're doing. So if you want to, from this course, you could take the prime number theorem as a black box, or as something that you can go and look at in a later course, or if you've already seen the proof of this, you can just use this as a starting point. But what I'm going to do is I'm going to start from a different place instead of the prime number theorem. We're going to start from something slightly weaker. It's called Chebyshev's theorem, which is almost the same. It says that the prime counting function, the number of primes less than or equal to x, is big O of x over log x. So what that means is it's basically the upper bound of the prime number theorem. The prime number theorem says these two functions should be the same size, and Chebyshev's theorem says that, well, we know that the prime counting function is no bigger than x over log x. And so we're going to prove this. The proof is really quick. Chebyshev gave a very slick proof of this fact. It's pretty neat, and that's what we're going to walk through. The start of the proof is this exercise that I've put up on the board here. It's an equivalence of upper bounds, basically saying that the prime counting function is big O of x over log x is an equivalent statement to the Chebyshev theta function, which is the sum of the logarithms of the prime numbers which are less than or equal to x, being big O of x. This is an exercise, and in fact, it's an exercise in Abel summation that I've put in the problem set. So this is something that I'm going to leave for you all to do on your own. We're just going to start from the Chebyshev theta function, and we'll prove this statement, that the Chebyshev theta function is big O of x. Okay, so how does the proof work? Well, it starts with a very clever observation by Chebyshev that you can use binomial coefficients to sort of pull out a sequence of consecutive prime numbers. So let's look at the binomial coefficient 2n choose n. So in case you don't remember the definition, that's 2n factorial divided by n factorial times n factorial. Now this number, we can look at all the primes that divide this number, and it's divisible by a lot of primes. It's a pretty big number. But at the very least, all of the primes that are between n and 2n have to divide this binomial coefficient. That's because any one of these prime numbers, they're smaller than 2n, so they're one of the factors of the factorial on the numerator, but these prime numbers are bigger than n. And because prime numbers can't be factored into smaller numbers, there's no possible way to have one of these primes showing up on the denominator, because the denominators it's a product of n factorials. So it only comes from factors that are smaller than n. So this binomial coefficient, in some sense, is capturing this long sequence of prime numbers. Now this is really nice because we can say something more about this binomial coefficient. This binomial coefficient is no bigger than 2 by the power of 2 to the n, or by the power of 2 times n. And depending on how comfortable you are with binomial coefficients, this might feel very natural or it might feel pretty out of the blue, so I'll just prove it real quick. 2 by the power of 2n is equal to 1 plus 1 by the power of 2n. And then the binomial theorem tells you that when you distribute 1 plus 1 by the power of 2n, it's equal to this big long sum. But these are all 1 times binomial coefficients, which are all positive. So 2 to the 2n is actually this binomial coefficient plus all the other ones. So it has to be bigger. Okay. So that's kind of cool. And then we can use this to get to the Chebyshev theta function by taking a logarithm of both sides. So taking a log of the left-hand side, log rules tell us that products turn into sums. So this is the sum of the log of prime numbers between n and 2n. Logarithms are increasing functions, so they preserve the direction of the inequality. And then the log of 2 to the 2n is 2n times log 2. All right. So this looks actually pretty close to what we want to prove. We want to prove that the sum over primes less than or equal to x of log p is big O of x. We have the sum over primes less than or equal to 2 times n, also bigger than n, is less than or equal to 2 times n times some other constant. That's almost exactly what we want. The only thing that's sort of off is we're missing all the primes below n. So if I write this in terms of the theta function, this looks like the sum of log p, where p is less than or equal to 2n, but we have to remove all the terms that come from primes smaller than n. We get this inequality. That's pretty close to what we want. And so now it's a matter of using this inequality and possibly some descent argument or some inductive argument in order to conclude that the theta function itself is big O of x, rather than a difference of consecutive values of the theta function. So I'm going to need an extra page to do this. And I'm going to prove this statement using a strong induction argument. So on the extra page, I'll rewrite where we had stopped. Which is this inequality. So strong induction. We will prove a little bit better than the big O statement. I had somebody asking me about effective versus ineffective yesterday. We're actually going to prove an effective statement, which is that theta of n is bounded above by 4n times log 2. We're going to prove this with strong induction. So for the base case, n equals 1. Theta of 1 is the sum over all the primes less than or equal to 1 of log p. But there are no primes less than or equal to 1. So that's 0. Which is definitely less than or equal to 4 times 1 times log 2, because one of those is a positive number and one of them is 0. Great. So now let's do the inductive step. So we're going to do this with strong induction. Suppose for all k greater than or equal to 1 and strictly less than n, that the statement we're trying to prove is true. And now we're going to try to use this in combination with this bounded difference that we've already proved in order to prove the same statement for n. And the way that we do this, we have to break it up into two cases. It depends on whether n is even or odd. If n is an even number, then I'm going to put a star next to this so that we know when we're using it. If n is even, then n divided by 2 is still an integer, and this difference is the same as this difference up here, just with a different value for n. And we get this kind of bound. So we rearrange. I don't know why it keeps doing that. And now we've bounded theta of n above by some constant times n plus theta of a smaller number. So the inductive hypothesis says we already know that for n over 2, that this statement is true. So this is bounded above by 4 times n over 2 log 2. That's by the inductive hypothesis. And, well, 4 times n over 2, that's 2n log 2 plus n log 2 is 3n log 2, which is actually a little bit better than what we wanted to prove. Definitely less than or equal to 4n log 2. So that's half of the inductive step. The inductive step works if n is even. Next, we have to check and see if it works when n is odd. So if n is odd, we can't start the same way, because n over 2 is not an integer. And we proved this statement up here only for integers n and 2n. Because if we go back to the previous slide, the role n played was it was the bottom of a binomial coefficient. And we can't plug in something into the bottom of a binomial coefficient that's not an integer. So we have to be a little careful for the n equals odd step. But what we can say n plus 1 is even. And in fact, I'm going to move this over. We're going to say more than n is odd. We're going to say n is odd and at least 3, since we already proved it for n equals 1. So that means n plus 1 is even and at least 4, which implies n plus 1 is not prime. Why is this important? Well, this is important because theta of n, which is the sum over p less than or equal to n of log p, is actually the same as the sum of p less than or equal to n plus 1 over log p, which equals theta of n plus 1. So this works out because the only difference between these two sums is possibly the n plus 1 term. But n plus 1 is not a prime number, and this is a sum of only primes. So really, we haven't changed the sum at all. N plus 1 is even. Oh, I need that to be a little bit lower. N plus 1 is even, and n plus 1 over 2 is strictly smaller than n. So we can use the relationship we proved on the previous slide once again. Theta of n, that's the same thing as theta of n plus 2, which is bounded above by, theta of n plus 1. It's bounded above by n plus 1 log 2 plus theta of n plus 1 over 2. And now I took a little bit more space than I expected, so I need another page. Let's see if I can just copy this without rewriting it. No, not really. Okay. So I'll rewrite that. We got this upper bound for theta of n. Again, the inductive hypothesis tells us because n plus 1 over 2 was smaller than n, that we get this upper bound. So once again, we get an n plus 1 log 2 here. The 4 and the over 2 cancel. There's 2n plus 1 log 2. We get 3 times n plus 1 log 2, which you can quickly check is less than or equal to 4n log 2 because n is bigger than or equal to 3. And that's easy enough to check. N equals 3 is the intersection point between these two functions as linear equations. And then 4n log 2 has a steeper slope, so it's going to go up faster than that. And that proves it in the n is odd case. And those are all the options for n. It's either even or odd. And we proved for both of them using an inductive hypothesis that the theta function is bounded above by some constant times n. That's big O of n. If you replace n by x, it's the same thing. All right. And now, like I said, I'm leaving it to you in an exercise to show that this is equivalent to Chebyshev's theorem for the prime counting function pi. All right, so that's pretty neat. We've got an upper bound for this function. We're going to use this as leverage to actually compute the asymptotic main term as a differentiable function for different sums over primes, rather than the sum of log p or the sum of 1. This next slide, we're going to look at this sum, the sum of log p over p, and we'll be able to prove, without proving the prime number theorem, that this is log x plus big O of 1. This result was known before the prime number theorem was actually proven. And so this, again, uses a clever trick, not the same trick as the binomial coefficient. This uses a trick involving factorials. So I don't know why I didn't write this out on the slide beforehand, but we're also going to start this with an exercise. This exercise was already in the Abel summation section of the problem set, but I put it in again at the prime numbers section of the problem set because we're going to use it right here. The sum of log n for n less than or equal to x. It's got a main term of x log x, a secondary term of minus x, plus an error term that's no bigger than log x. So we're going to assume this. And once again, this is a good exercise for working with Abel summation. This is something that you can prove using Abel summation. All right, so how are we going to do this? We're going to look at n factorial instead of the binomial coefficient like we did for Chebyshev's theorem. We'll write n factorial in two different ways. The first way, n factorial, well, it's a positive integer, so it has some prime factorization. The second way, n factorial is the product of all numbers, all positive integers less than or equal to n. These are the two ways that we are going to write out n factorial. So we need to say, what is this exponent? How many times does a prime number divide n factorial? This is a nice exercise. You may have seen exercises like this before. Questions like, how many zeros does 200 factorial end with? That's this kind of question, finding the exponents of the primes in the prime factorization, specifically the exponent of 2 and 5. The minimum of those two numbers will tell you how many zeros n factorial ends with. All right, so n factorial is the product of all numbers below n. So we might say, all right, well, we're going to get a prime factor p for every number less than or equal to n that's divisible by p. Well, that is n over p floor function. So this is the number of, running out of letters here, d less than or equal to n, such that p divides d. Okay, but this is not the only place where we can get prime factors. What if p squared is one of those numbers less than or equal to n? That won't contribute only one divisor, that will contribute two prime divisors. So that should make the exponent bigger. So we have to add another term, n over p squared. This is the number of d less than or equal to n, such that p squared divides d, because every time p squared divides d, that doesn't add just one factor of p, it adds two factors of p. And in fact, this pattern continues. We have to do it for p cubed, p to the fourth, etc., giving us this infinite sum formula for expressing the exponent of these primes. Now I say infinite sum, but technically this is not an infinite sum because we have these floor functions here. Eventually, you'll find a power of p that's bigger than n, which will make this fraction less than 1. And so when you put it into the floor function, it will become 0. So the way we write out this explicit formula, it's written out as an infinite sum, but it's secretly a finite sum because all but finitely many of the terms are secretly 0. Okay. So going from here, again taking the logs of both sides, we get the log of the prime factorization looks like this. The log of the product of all the integers less than or equal to n looks like this. But This sum is actually the same as the one that I gave you in the exercise. We already know what that looks like. That's n log n minus n plus big O of log n. So we've gotten pretty close. This sum of log p times whatever these exponents are, this long sum of floor functions, we know that this expression is n log n minus n plus big O of log n. And in fact, I can fill in a little bit here. We know that the exponent is only non-zero if we're looking at a prime that's smaller than n. That's because n factorial is only ever divisible by primes that are smaller than n. In fact, you could also do that by arguing these floor functions. If the prime p is bigger than n, then all of these fractions will be smaller than 1, and so their floor will always be 0. So this sum really is only for p less than or equal to n. Okay. So I'm going to take this, rewrite it on the next slide. Oops. I need to do an extra slide. And in fact, I'm going to write out what the exponents are. We've got log p times the exponents in the prime factorization. And this is equal to n log n minus n plus big O of log n. So how are we going to take this and actually figure out the sum of log p over p? That's our goal here. Well, if we look at the leading term, that looks like log p over p, sort of. It's got a floor function, which throws things off a little bit. It's got an n here, which throws things off a little bit. But if we could get rid of both of those, the leading term there looks like it's the right thing. So let's check the leading term. This is a pretty similar computation to what we have been doing with the floor function in the past. The floor function is equal to whatever's on the inside with an error of big O of 1. So we multiply all this out. The first term, we can factor the n out, and we get the sum of log p over p for p less than or equal to n, which is the sum we want to consider. And it's only off by some error, which is big O of p less than or equal to n log p. Now here's where we use Chebyshev's theorem. Chebyshev's theorem tells us that the Chebyshev theta function is big O of x. But that's exactly what we have written here in this big O. The sum of log p for p less than or equal to n, that's big O of n. It's no bigger than a constant multiple of n. So what we found is the main term looks like this. Where here I use Chebyshev's theorem. So we got the log p over p summation that we were looking for with a factor of n, but that's okay. And the error is big O of n. Okay. So that's the main term. What about everything else? Well, everything else, it's going to turn out, belongs to the error. And this is going to be a pretty common theme that you'll see in analytic number theory in this course, or if you go on to other courses in analytic number theory, which is that larger powers of the primes don't affect the main term. It doesn't affect the rate of growth of your function. It's really only the smallest power of a prime that's going to make a difference in what you're computing. So let's see why that happens. So all the other terms starts from p squared, p cubed, etc. Floor functions are bounded above by whatever's inside the floor, because the floor function is just the greatest integer that's below the thing you plugged in. So we can bound this above by basically dropping the floor function. So we get log p, and then it's times the sum from I equals 2 to infinity of n divided by p to the I. Well, that's a geometric sum, right? Starting from I equals 2. If you use the geometric sum formula, you get n over p squared divided by 1 minus 1 over p. And if we multiply this all out, I'll pull the n to the outside. Sum over p less than or equal to n log p divided by p minus 1. That's what happens when I simplify all those fractions. Okay. So what's so useful about that? This series converges as n tends towards infinity. So this is something that I'll leave mostly as an exercise. My hint is that you should be able to compare it with the sum of 1 over n to the 3 halves or something like that. Because what's happening in this series, the denominator is a quadratic polynomial. So the denominator acts like p squared or n squared. The numerator is a log function, which acts smaller than any power of n. So you should be able to bound it above by something like the square root of n or the square root of p. And then when you do that kind of comparison, you can compare it with a convergent p series. So what that tells you, this is a convergent series of positive terms. It's bounded above by the limit of the convergent series. So this entire thing is bounded above by n times the value of a convergent series. That's some constant. This is big O of n. Oops. There we go. And so we see that all the stuff that's left over belongs to the error. It's no bigger than the same error term from our leading term piece. Okay. And so then the very last step is to take these two expressions and replace them in this equality that I've written on the top line. So that is what we'll finish on the next slide. So we reduced the left-hand side to the leading term piece plus all the other terms equals the n log n minus n plus big O of log n. Now we divide everything by n so that we can get the sum by itself. This is plus big O of 1 plus big O of 1 equals log n minus 1 plus big O of log n over n. And now it suffices to look at all of these extra terms and show that these are no bigger than our desired error term of big O of 1. Certainly this is the case. Big O of 1 is big O of 1. Minus 1, that's a constant. So constants are bounded above by other constants. So that's also big O of 1. And then log n over n. As n tends to infinity, log n over n tends to 0. This is something that you can prove using L'Hopital's rule. And so as n tends to infinity, this is tending to 0, which means eventually it's smaller than 1. And so that's enough to say it's big O of 1. And that's what we wanted to show. We were trying to prove that this sum of log p over p is equal to log n plus big O of 1. All right. So we're starting to see with these problems that the work is getting a bit more involved. Chebyshev's theorem and this theorem, they both started with a neat trick, doing some binomial coefficient or some factorial trick. But even after we did those tricks, the work after that in evaluating the sums was a little bit longer. I took a whole slide back here after doing that trick in order to simplify this left-hand side and determine what's leading here and what's not leading. Once you start working with prime sums, this can start happening because we know less about prime numbers than we do about integers. And so you might have to start doing a little bit more, deciding, well, what terms are important that you really should be studying, and what terms can you shove into the error term sort of one at a time to ignore them. And we can see sort of the big result, Chebyshev's theorem, right here that we used. It's good to have like a library of really big results to think about when you're doing these types of sums. All right. And so the last thing from this section is the harmonic prime series. We can use the result we just proved, that the sum of log p over p for p less than or equal to x is log x plus big O of 1, to prove that the sum of 1 over p for p less than or equal to x is log x plus big O of 1. So this I'm going to leave as an exercise to you. The proof is using Abel summation, but it's all about prime numbers now. It's a sum over primes and not a sum over integers. And so this will help you get a little bit more comfortable with the results that we've already proved in this lecture. Now we're going to use this corollary a few times for the later sieves that we're going to talk about. And with the exercise, I've even told you how to get started with Abel summation. And so just briefly, before we start talking about the next section, this is one very long way. There are much shorter proofs. This is one way to prove that the sum of 1 over p for p prime diverges. There are other shorter proofs of this fact, but this is a pretty interesting result. It's one way that you can prove that there are infinitely many prime numbers, because a sum over the prime numbers of something is divergent. You can do the same thing with log p over p instead of just 1 over p. But somehow having the harmonic series, relating this to the harmonic series 1 over n is kind of a nice looking result. And you prove this by just taking x to infinity in the above result. Log x will tend to infinity, and big O of 1 is bounded by a constant, so there's nothing to cancel out the infinite term. All right, so let's pause for a minute. We're mostly out of time. I'll briefly be able to start talking about the next section, but let's pause for a minute and see if anybody has any questions about prime numbers or any of these things.
Brandon, no questions so far, but I'll let you know if some question comes up.
Okay. All right. So then the next section, which we're only going to sort of briefly be able to start talking about, and we'll spend most of the time in the next lecture talking about it. We're going to go back to the sieve of Eratosthenes. So remember, this is the sieve that I gave in the very beginning of the mini course, in that introduction, the sieve for finding prime numbers. Well, we can talk about this a little bit more explicitly and try to use it to count primes. Now, the sieve of Eratosthenes is actually not any better at counting primes than Chebyshev's argument was that we just went over today. But the ideas in the Sieve of Eratosthenes are very important and play big roles in other more advanced sieving techniques. And so this is why I want to go through this sieve in detail. So here's how we're going to start this. We're going to ask questions about this function, phi of x comma z, where this is the number of integers less than or equal to x, such that those integers are not divisible by any primes below z. So one thing that we can think about this is like an intermediate step. Of the sieve and the introduction. We've already eliminated all multiples of some collection of small primes. We want to know how many numbers are left over. Maybe we haven't finished the process. Maybe, for instance, z is equal to 4, and we've only eliminated multiples of 2 and 3, and we want to know how many numbers there are that we've eliminated. This is like at each step of the sieve, asking, okay, how many do we have left? Have we gotten better? Has somehow our method gotten worse? Those kinds of questions. So here I have on this slide a theorem that we can pretty quickly prove that tells you how big this function is. And so what we've got here, it's x times this product plus some error term. So we're going to say a couple of things about this product right here. So let's talk about the product first. This product is certainly below 1 because, well, it's a product of things that are smaller than 1. And we know if you multiply two numbers that are smaller than 1, it gives you something that's still smaller than 1. But in fact, we can say a lot more about this product, and we will say more on Thursday. But I'll just tell you right now, as z tends to infinity, this product tends to 0. So if z is very large, this product will be very small. And if you can make z get large at the same time x gets large, we can actually say that the main term grows strictly slower than x. So that's going to be the goal. We're going to try to say, well, let's make z grow with x so that we can actually reduce the size of this main term and say, okay, we've got a bound for the number of integers that are left at this step of the sieve. Now, the big thing standing in the way of that, I'll do this in a different color, is big O of 2 to the z. This is our error term. And if z is growing with x, that means this error term is also growing with x. And 2 to the z, it's an exponential function. That grows really fast. This grows very fast in z. That's a problem. If z is too big, big O of 2 to the z will be bigger than the main term, which I'm putting in quotation marks, because if the error is bigger than the main term, it's not really a good main term, is it? For example, if we picked z equals x, so in this function, we take all integers below x, but then we remove all the integers that are divisible by primes below x. Well, we know reasonably that that should get rid of all the numbers because every number is divisible by primes below x, but this theorem would have an error of big O of 2 to the x, which is huge, way bigger than the main term, and it basically tells us nothing. We started with x integers, and this theorem says, oh, well, out of those x integers, you have at most 2 to the x of them left over. Well, I could have told you that without any work. 2 to the x is bigger than x. It's not surprising that we have that as an upper bound. And so this error term being so large says that this theorem is not significant unless z is very small. So what would be a significant value for z to plug in here? Some possible example. Let's go back to black. Example of a significant value. We could let z be log x, because then big O of 2 to the log x, exponentials and one of the logs will cancel out up to a constant multiple, because this is log base e. But up to that constant multiple, this is big O of log x. That's pretty small. And so we really will have that, hey, big O of log x, that's less integers than we started with. And so all it takes is for us to look at the main term and ask, well, what does this look like? So this grows like what? So if we want to do an early step in the process where we've only eliminated primes below log z, this theorem is significant. It tells us actually something meaningful about how many numbers are left over. It's not a trivial statement. All right. So it's about 2:21. So why don't I just tell you what the plan is for Thursday and for my overflow lecture. On Thursday, we'll prove this theorem. The proof's not very long. And we'll talk a bit about this product. How do we figure out how big this product is? How do we understand the growth of this as a function? And then we'll go through, the section's a little bit longer, we'll go through the sieve of Eratosthenes in detail. We'll talk about methods to improve this error term. Big O of 2 to the z is not the smallest that we can make that. We can do much better than that. And we'll state a general form for the sieve of Eratosthenes. There's a really nice homework problem in this section, which maybe wait until Thursday to work on. I'll talk about it more then. And that'll be the focus for Thursday. And then I'll have one overflow lecture, probably be about 50 minutes. I'll record it in private, and then I'll have Alvaro post it to the YouTube channel when it's done, probably sometime over the weekend. The overflow lecture will be about Brunn's sieve. So this is a more powerful sieving technique, which can be used to prove some non-trivial results about problems like the twin prime conjecture or gold box conjecture. We won't go through the entire proof of Brunn's sieves because they're kind of long, but we're going to talk about the big ideas and some of the major steps in those proofs, what the results look like, why these results give improved error terms or improved main terms, and things like that. All right, that's it for today. Anybody have any questions?